Hey friends, welcome to chapter 11. This chapter is going to be a little bit different than what we've done so far in this book, so that's the welcome change. So it's chapter 12. Actually, everything else from now on is going to be a little bit different than the regular algebra too. We are starting sequences and series, and we're going to learn all kinds of stuff about all kinds of rules. Let's start with the sequence and what a sequence is, and that is a way numbers are aligned to where you have a first term, a second term, a third term, a fourth term, and so forth. I have two different sequences aligned here for you. 3, 6, 9, 12, and 15. And the exact same thing, the only difference in between them is one doesn't have anything after 15, and the other one has dot, dot, dot. The one that ends with nothing in here would be a finite sequence. The one that says dot, dot, dot is to suggest to you there's more numbers coming, so this is an infinite sequence, okay? We call this. We are going to use the name AN to determine the nth term. What do I mean by this? First term is 3, so I would write that A1 is 3. My second term, or A2, is 6. My third term is 9, and so forth. So this little number, it tells you which place in the line, in the list, your number is. So that n, it's going to be which term of your sequence it represents, okay? Now, each sequence will have a rule every single time, and the trickiest part about this would be to figure out the rule. So I'm looking at this and I go 3, 6, 9, 12, 15. And as we practice, it's going to come more normal. But if I look at this, I can write this as 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5, right? So notice something. My rule would be 3 times. This is my first term. This is my second term, my third term, my fourth term, my fifth term. So it's going to be 3 times n. No matter what, if I would say, what is the 8th term in here? Would be 3 times 8. It would be 28. And let's continue to say this is 5th. My 6th would be 3 times 6, 18. My 7th would be 21. My 8th would be 24, right? Because we just increased by 3. There's a different rule that you can put, but that would be hard. This is 3 plus 3, this is 3 plus 3 plus 3, and so forth. But it would be too confusing. So really just look at it as 3 times 1, 3 times 2, 3 times 3. Always find the easier rule. So in this case, it would be 3 times n. We said an represents your nth, that little n represents your nth term. We also have two different notation. You can name it as an, or you can name it as f of n. Either way we'll go. That would be a function notation. This would be just a sequence notation. But let's look at some things that they ask us to do in example 1. So we see how we work on that. You have this, it says, write the first 6 terms of the sequence, and here they give you the rule. an is 2n plus 3 for the first one. So I'm looking for a1, which would be 2 times 1 plus 3, or 5. a2, which is 2 times 2 plus 3, which is 7. a3, 2 times 3 plus 3, it's 11. It's 9, don't listen to me. a4 equals 2 times 4 plus 3, this is 11. a5 is 2 times 5 plus 3, which is 13. And then a6, it's going to be 2 times 6 plus 3, which is 15. And I wrote the first thing. And I wrote this a notation of a sequence. What if we look at the next one, and the way they say it to you is f of n equals -2 to the n minus 1. Well, it's going to work the exact same way. F of 1 equals -2 to the 1 minus 1, or -2 to the 0, which is 1 always, right? F of 2 is -2 to the 2 minus 1, -2 to the 1, which is -2. F of 3 is going to be -2 to the 3 minus 1, -2 to the second, which is 4. F of 4. And I'm going to stop because I'm wasting your time because I think I understand how it goes. Whatever this becomes, it's going to become your n, right? Whatever that term is. So this is the notation that we're going to play with over and over and over again, okay? Now, each sequence will have a rule, and or a pattern. We call that a rule. So the trickiest part of this would be to learn how to read those patterns or those rules so you can actually write them as a formula. So if you are on page 652, it says describe the pattern for negative 1 over 3, 1 over 9, negative 1 over 27, 1 over 81, if I'm not wrong. And then it says dot, 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 dot. First of all, this is an infinite sequence because we have the dot, dot, dot that is following it. And we want to know the rule of this. And here's what I noticed. If you pay attention to this, this is 1 over negative 3 to the first power, 1 over negative 3 to the second power, 1 over negative 3 to the third power, 1 over negative 4 to the negative 3 to the fourth power. And one of the things that I want you to always look at this, whenever you have a plus, minus, chances are the first thing you want to visit is an exponent rule. Because if you remember, a negative number to an odd exponent will be negative, and to an even exponent will be positive. So really this becomes did I write I'm curious, A of n. A of n is going to be 1 over negative 3 to the nth power. So depending on what that is, it's going to become this. They have it written in the book as negative 1 over 3 to the n power. It would really be the same thing because 1 can be written as 1 to the n power. But if you write it like this, because you notice that change, it works also. Okay? This is how I looked at it. And I am not looking at the book. I really am teaching you how to read sequences as you look at them. So, let's look at the next one. The next one is this. 2, 6, 12, 20, dot, 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 dot. And this is going to be a tricky one to look. The first thing I would always advise you to do is minus it and see if you have a way to do it this way. It doesn't work this way. 6 minus 2 is 4, 12 minus 6 is 6, 8. It doesn't really connect. So I'm looking at this and I'm thinking, okay, I can't add the same number. Can I multiply? This can be written as 1 times 2. This can be written as 2 times 3. This is 3 times 4. This is 4 times 5. Right? So I'm looking at this and I'm going, as a thought process, this is my first term, this is my second term, this is my third term, this is my fourth term, which means this is my first term, n, times the one that follows after him, n plus 1 every single time. And you will work with anything. If I would tell you what is the rule or what is the, I'm trying to think, 7th term, this will become 7 times 8, which is 56, right? So this is going to be a little bit of a work until you get to learn how to read patterns. But it will come eventually naturally, and we'll work at it as much as we need. Now, try to graph a sequence. We're not going to worry about it too much. We are going to learn how to write the rule from it. In example 3, you have a pyramid of fruit, and really, here's what I have. The top, it has 1 orange. The next one is 4 oranges. The next one is 9 oranges. The next one is 16 oranges, and so forth. So first thing we need to know is, what is this rule? So I'm looking at this. 1, 4, 9, 16. I can't add, I can't subtract. But I noticed that 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, and this is 4 squared. Every time you think of a rule, think about the fact that this is the first term, the second term, the third term, and the fourth term, which means, can I bring it back to this number? And I could. Look at this. So my series is an equals n to the second. So if we would need to graph this, your graph would look like this. It's actually a parabola, but we're not using negative numbers. And you will not be a negative, yeah, it will be a parabola because it's n to the second, and that's kind of how it goes. This being oranges and being a real life problem, we cannot have any negative 2 oranges. So this is why your graphing there only has 1 by that, because real life problem, no negative oranges. But this is how you read stuff on sequences. And now, we covered this part. We're going to go ahead and work on series. So sequences deals with a list of numbers from the first term to the nth term. We're going to always try to find the rule and work with that. For series, it says says here, when terms of a sequence are added, the resulting expression is a series. So if I have a sequence, I have what we just had, 3, 6, 9, 12, and 15. And I'm not going to write the other one because one is finite, one is infinite. If I do this, this is a sequence. It can be finite or infinite. 3 plus 6 plus 9 plus 12 plus 15 is called a series. Okay, that's the difference in between them, okay? And then the series, you have the same thing. If the sequence is finite, series is finite. If the sequence is infinite, the series is infinite. How do we mark that? With this beautiful sign that it's called epsilon. It's a Greek letter, and it means sum. And this one, you always tell you, where do you start, where do you end, and how many terms do you have? Let's look at this one. I start with, and they name it I, which is confusing since we moved from n, but you start with I equals 1, and I go 1, 2, 3, 4, and I have 5 terms. I count how many I have. I start at 1, I have 5 terms, and then do you remember the rule for this one? This was 3 times 1, 3 times 2, 3 times 3, 3 times 4, and 3 times 5, so this is 3 and really you put this sum symbol, and then you put in your rule for that particular notation. That is called sigma. Oh, it's not epsilon, it's sigma. I was wrong. It's a Greek letter, and it means sum, and that's how you write it, okay? Now, the difference in between this being a finite or infinite, let's say now, for the sake of it, this is infinite, you work the exact same way. You start at I is 1, or you start with your first term, but you don't know where it ends. It ends at infinite. 3n. Okay, it's the same thing, but now you can't tell it I only have 5 terms. I have as many as I choose to, so we use that notation. So let's look at example 4 in your 11.1 class, and it says, write each series with summation notation. And here's what you start. 5 plus 10 plus 15 plus plus 100. And then I don't have any dots after it. So this is a finite series. The first thing I need to know is what is the rule. I need to know what the rule of this sign is. Well, this is 5 times 1, 5 times 2, 5 times 3. I'm assuming you work on times to 5 times 20. And, remember, I like that because I know how many terms I have. I can now write as sigma, when I is 1, all the way to y is 20 of times 5n, or how many I have in there, right? Or 5i if we're going to use I in here. Sorry. So finite, it starts at 1, ends at 20, and it's 5 times each term. Now let's look at the next one. The next one is 1/2 plus 1/3, right? Yes. No, 2/3. 2/3 plus 3/4 plus 5/6, blah, 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 blah. Actually, 4/5 first. Let's skip one. And I now know this is an infinite series. And so I'm going to write this. I starts at 1 and it goes to infinity. I don't know what it is. I need to look at this rule. Remember, this is my first. This is my second term. This is my third term. This is my fourth term, so forth, which means this means my nth term over this plus 1 every single time. 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. So it's going to be n plus 1. So my first term would be 1 over 1 plus 1, which is 1/2. My second term would be 2 over 2 plus 1, which is 2/3, and so forth. So this is going to become I plus 1. If you're wondering why n and I is because the sums are notated by I. I don't really know why. It would have been a lot easier to use them as n's. But that's kind of how it works, okay? This is where we are. Finite, infinite, and you get to write the rule accordingly. Let's move on to the last part of this lesson. This is a little bit of a longer video. The next one should not be that long. And it says, find the sum I equals 1 all the way to 6 of 2i. Well, this is 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5 plus 2 times 6. And you get to do all of this wonderful math. It ends up being 42. Use a calculator, use your mental math. It doesn't matter what you use. Let's look at the next one. And keep in mind, this I can be any letter, so don't let it throw you off when you do something like this. K equals 1. Now it starts at 3, and it goes to 6, right? So, and your rule is 2 plus k to the second power. And you start at 3 and you go to 6. This is 2 plus 3 to the second power plus 2 plus 3 to the third power plus 2 plus 3 to the fourth power plus 2 plus 3 to the fifth power and plus 2 3 to the sixth power. All of these are in order. Whoa, no. 3, 4 to the second, 5 to the second, 2 plus 6 to the second. Why? Because k starts at 3, and then it becomes 4, and then it becomes 5, and then it becomes 6. You go from 3 to 6 each time raising to the second power. And then you can do this in your calculator if you need to, and this ends up being 94, okay? All of these examples are in your book at 654. I really messed this one up. I got super excited. Now, on page 654, you have formulas for special series. And this is going to become your cheat sheet. I'm not going to make you memorize this formula. So make sure you start on your cheat sheet and write stuff down for those formulas. And then we're going to use just using a formula as a sum. It says, how many oranges are in the stack in example 3? So if we would move all the way to the bottom, it tells you that that pyramid has 10 layers, right? So we know there's 10 layers. My sum is sigma. I start with 1 because there's only 1 on the top, and the bottom square is going to be 10, so it's go all the way to 10. And if you remember how we wrote this rule was, it was n squared at the time, but now it's I squared. And now I need to go and add 1 squared plus 2 squared plus 3 squared plus 10 squared. Where is this very beneficial? Is when you look at, let me look which formula we're using, which is formula number 3 on that little thing. If you actually have a formula for y equals 1, I equals 1 to n of I squared, this becomes n plus 1, n plus 2, all over 2n plus 1, sorry, 2n plus 1 over 6. So how many times do we have here? We have 10, so this becomes 10. 10 plus 1, 2 times 10 plus 1, all divided by 6. This becomes 10 times 11 times 21, all over 6. And this becomes, if you do all of the math, well, 3 and 5 and 7, 55 times 7, 385. If I butchered it, I did not. There's 385 in that stack. So look at those formulas because you're going to want to use them. A sum that starts at 1 and goes to m of 1 is that many because it's 1 plus 2 is how many there. A sum that starts at 1 and goes to n of I numbers, it will be as many numbers you have times that numbers plus 1 divided by 2. And we worked kind of this in class. And then the third one is the one that we just used in here. So this is your 11.1. Happy homework, and I'll see you 11.2.